Good day, everyone. In our previous topics in magnetism, we focus on calculating the amount of force on a moving charge or charges in a conductor in the presence of magnetic field, which means that there is a magnetic field in the surroundings, and here comes the charge, travels on it, and we calculated the amount of force experienced by that moving charge or charges. Now, in principle, in the theory of magnetism, all moving charge particle generates magnetic field in the surrounding space. Okay? Now, on those topics that we discussed previously, we ignore or we silently disregard that idea of having a magnetic field produced from the moving charge. Now, in this chapter, let us now focus on how much magnetic field produced by a moving charge, which means that we will calculate what is the magnetic field in the surrounding space because of the moving charge particle. Now, we call this as the sources of magnetic field. And we will focus on the study of the magnetic field in a moving charge particle, meaning single charge particle. Now, to start with, let us recall first the idea of electric field in electricity. Take note that if we have a charged particle, let us say a positively charged particle, we understand that there is a spread in the surrounding. We call it as charge distributions. And that charge distribution generates electric field. Meaning, an stationary charged particle is placed on a space at rest, then it will generate the charge distribution is called as the electric field, which means that at any point in the space, let us say point P in the three-dimensional axis, there is an electric field at that point. So in order to calculate, we should know what is that point, where is that point, meaning what is the position of that point in order to calculate the electric field. So that electric field can be calculated using only the charge, the magnitude of the charge and its distance from that point. So therefore, electric field can be calculated, and we understand that the electric field is directly proportional, of course, to the magnitude of the charge and inversely proportional to the square of that distance from that source charge. And then the formula says that the electric field at that point is 1/4 pi permittivity as the electric constant multiplied by the absolute value, because we are taking only the magnitude of the electric field, although the electric field is vector, so we are only concerned with the magnitude of the electric field, then it should be Q over R squared. Okay? Now, for a vector quantity, then electric field is vector is 1/4 pi permittivity Q, absolute value of Q, divided by the R squared, multiplied by the unit vector pointing the direction of the electric field, which means that we can always calculate the electric field provided that we have the charge and we have the position in space of that point of interest. So we need only two informations for the magnitude, the charge and R. Now the unit vector is required if we are calculating the unit vector or the vector field, electric field. Okay. Now, the unit of the electric field, remember, is Newton per coulomb, or you can use volt per meter. Then, the electric constant is very easy, 1/4 pi permittivity. It is equal to, since constant, 9 times 10 raised to 9 Newton meter square per coulomb square. Okay, now, what about in magnetic field? In magnetic field, if we have a moving charge, remember, it is not at rest. it is not stationary, it is moving charge. Okay, so suppose the particle, charge particle travels with velocity, then that by principle, that charge generates magnetic field in the surrounding space. Just like electric field, but the electric field is placed at rest at the space, then it generates electric field. As long as there is a charge, there is always a magnetic field. But in magnetism, the moving charge particle, meaning it is not resting, it should be moving, it will generate magnetic field. So our task now is how much magnetic field produced from a moving charge. So we ignore the force, okay? We focus on how much magnetic field at any point in space, call it as P. So the question is, what is the magnetic field at P at a distance R, position R? Sorry, this is position R. No, the unit vector is same direction. Okay. Now, we should know, in that case, we should know the angle from the direction of the velocity towards that line of interest, meaning the position vector. So it is required to know how much is that angle away from what? From the velocity. Or you can express the velocity in terms of I hat, G hat, and K hat, and you can express the unit vector or the vector position in terms of I hat, G hat, and K hat. Okay? Now, the question is, how much is the magnetic field? Now, remember that because of this area produced by, because of the direction of the velocity and its position, we have that angle, then it has the velocity and r are lying on the same plane. That's the theory. Meaning the angle P or theta or P is within the plane. Now, perpendicular to that plane, there is a magnetic field at point P, which is directed perpendicular to the generated area, this area. Now, you can use your right hand rule, holding the direction of the current. Then you have to curl your finger, then stretch your thumb towards the direction of velocity. Then that curl of finger will be the direction of your magnetic field. And of course, it is a circular. It is a circular, because we learned our experiment in magnetic field about the conductor. We informed that the magnetic field is circulating around the conductor. So in same way that the particle travels in direction of velocity, you can use your right hand rule. Then the curl of your fingernails will be the direction of your magnetic field. And of course, it is a straight line. It should be tangent to that curve. So in that case, the magnetic field is actually normal to this plane at that instant. Of course, at different position, different orientation of your plane. But at that point, that magnetic field is perpendicular to this plane. Okay, so we want to know how much is that magnetic field produced. Remember, this magnetic field is the magnetic field produced by this moving charge in the direction of this velocity. And we are interested at that point. Of course, we need that R. Okay? Now, by principle, that magnetic field is directly proportional to that charge. Meaning the moving charge, still directly proportional to that magnetic field, vice versa. And also, proportional to the velocity component along the because this is sine, because therefore the V sine P is the vertical, okay, or the opposite, the y component of the velocity, because it is sine P. Meaning you can see it here, the component of velocity might be, for cosine, it should be the parallel to that velocity, but the sine function is perpendicular to that. So therefore, the magnetic field is proportional to the charge and proportional to the velocity, of course, but it is the component along y, which is sine p, and inversely proportional to the square of what? Of the position vector. So this is quite similar to the electric field, directly proportional to the charge and directly proportional to the square of the position. But in magnetism, the magnetic field is proportional to the charge, proportional to the velocity, and inversely proportional to the square of the position. The position, remember, is the point, our point of interest direction. Okay? So to make this as a formula, in order to calculate, the magnetic field is equal to mu naught over 4 pi, where mu naught is the permeability of empty space. Take note, permeability. Now, in our electricity, we have the so-called permittivity. The permittivity is, remember, in electricity is the property of a vacuum that allows the electrostatic effect that passes through that region. But the permeability is the amount that of the electrostatic or the magnetic effect that percolates into that surface, into that space. So, permeability versus permittivity. The magnetic field is talking about the permeability. Okay? So, the permeability over 4 pi, we call it as the magnetic constant. So, if we multiply that with the charge, absolute value of the charge, and the velocity component along y, that's why b sine p, over r squared, it is the magnitude of the magnetic field that generates by this moving charge. Okay? So, what are the requirements to calculate the magnetic field produced? Remember, take note, produced by the moving charge. The answer is, we have the magnetic constant, mu naught, or the permeability divided 4 pi, the absolute value of the charge, then v sine p r squared. Take note that p is the angle from, it should be from, the velocity towards the position vector. So that plane is along the plane generates by the velocity and its position. Okay, then the magnetic field should be perpendicular to that. So you can imagine a paper. This is we have the paper. Normal to this, normal to that is the magnetic field direction. Okay? So very important to know what is the angle from the velocity towards the position, because that plane perpendicular to that is the direction of your magnetic field. Yeah, in a right hand rule. Okay? So if this is your plane and this is your magnetic field, you take the curl of that, it should be the direction of your magnetic field using right hand rule. Okay? Now, we call this as the magnitude of the magnetic field. Now, the vector, of course, remember that R is a vector and V is a vector. So, if you take the cross product of the velocity and the position vector, the unit vector, multiplied by the constant and the charge, divided by the R squared, the magnitude of the position, we call this as the magnetic field vector. So this equation is the magnitude, while this one is what? The magnetic field vector. So the requirement to solve for the vector is you should have the velocity vector. So of course it can be I hat in terms of I hat, j hat, or maybe k hat, or both. Then you have to take the cross product of the unit vector. So remember your unit vector. the vector, position vector r divided by its magnitude is a unit vector. So you have to identify the the position vector as we did in our electrostatics. So calculate or find the unit the vector position r vector, then divide its by magnitude, and the answer is the unit vector. Okay, so then that result should be crossed from the velocity vector. Then this one are constant. Charge is constant, it will not change. But remember, you have to consider sign here, no? In the magnitude, you take the absolute value, but in the vector, you have to consider the sign. Positive, positive, negative, consider the negative. That's for calculating the vector field, magnetic field. Okay, then this R is the magnitude of the position vector. Okay, so that's it. These are the formulas. Then take note that the R hat, recall that it is the vector over the magnitude. Okay, or you can say it without arrowhead, then take the remove arrowhead, then take the absolute sign, then this is the magnitude of R. Okay, then there is an option, meaning you can replace this R hat to this formula, then simplify, then this will be the result. If you are using R vector, then you can take you can cross it from V, then your denominator R should be cube. But if you are using unit vector of that position, your R is squared only. Why? Because we just substitute this unit vector here. So of course R becomes cube because this is R, and this one becomes a vector. So there are two ways to do it. Okay, it's either of these two. You can find it by consistently use the formula. So any of this you are free to use this formulas. Okay, then these formulas, we call this as the law of biot-savart. They are the physicists, no, who provide formally this idea of calculating the vector. So every time that we calculate the magnetic field, the source of magnetic field, the idea is coming from the law of biot-savart. Okay, so meaning if this point will travel, if you take the curl of your fingernails, then this will travel in this position, and this is R, then your vector field, your magnetic field will change its direction. But if this position vector has the same magnitude of this position vector, then the amount of magnetic field here is the same as the magnetic field. The only difference is the direction because of the position. Okay, that's it. So at any point, if you rotate that in a circle, complete circle, this magnetic field are the same. Okay, and take note that the magnetic field is inversely proportional to the position, the magnitude, the velocity, the position vector or the distance, and directly proportional to the velocity. The greater the velocity, the greater the charge, the greater the magnetic field. But the farther the point of interest, the smaller the amount of magnetic field. But if you are looking for the magnetic field very close to the moving charge, the magnetic field is increasing and increasing, and it is a maximum at the surface of the moving charge. Okay, so that's it. Now, if you are asked how much magnetic field in the direction of the velocity, meaning you are looking for what is the magnetic field at this axis line wherein the particle travels, the answer is 0. Okay, why? Because we look at the formula. If you are looking for the magnetic field at this position, which is parallel to the direction of the particle, then the angle is 0, and the sign of 0 is 0. So therefore, the magnetic field at the center of the curling magnetic fields. At the center, the magnetic field is 0. Okay, so that's it. Then, if you are looking for how much magnetic field, by the way, if you look at these situations here, if we have the observer at this point looking at the direction of the moving charge and the magnetic field, you can see this orientation, which means that you are here and looking at the moving charge moving away from you. This one, that's why this is x, and this is velocity. And this magnetic field is approximately at this point. Okay, this is your point P, and this one is might be here at this point. Then if you continuously rotate, we have a magnetic field here and this one, and this is the same magnetic field because they have the same position. The difference are the direction of the magnetic field, and it is again curling magnetic field. So the magnetic field at this point is 0. So if you take closer and closer at this axis of rotation, this magnetic field is what? Will keep on smaller and smaller. Okay, which means that the greatest magnetic field, remember, produced is at 90 degrees. So at this point, with the same axis, the magnetic field here is of course greater compared to that, because the aside from the other closer, and the angle is greater than, so the angle must be from 0 to 90. Okay, 0 to 90, and it is increasing towards 90 degrees. Okay, now the constant, remember again, mu is the permeability of the vacuum. Then it has a magnetic constant. Mu, the mu naught over 4 pi is just equal to 10 raised to negative 7. Very easy. And the unit is Tesla meter per ampere, which means that this mu naught over 4 pi, just replace this with 10 minus 7. This is the same as for electric constant. The electric constant, which is 1 over 4 pi permittivity, is 9 times 10 raised to 9. But for the magnetic constant, the mu naught over 4 pi is equal to 10 raised to negative 7. So you have to memorize this. Very easy. Replace the mu naught over 4 pi by 10 raised to negative 7. And the unit, one of the unit can be Tesla meter per ampere. Of course, we have another units as we move our discussion. Okay, so talking about the units, mu is, remember, the vacuum permeability or the magnetic constant. So 1 unit of this is, it can be Newton secant squared per coulomb squared. Then this is also equal to 1 Newton per amp square, or it can be Weber per amp per meter. Then it can be Tesla meter per area. Okay, so these are the different units that can be used for the vacuum permeability or the magnetic constant. Now, to be exact, numerical values. The mu naught is 4 pi times 10 raised to 7, and any of these units will do. Okay, so just the mu naught is 4 pi times 10. That's why if you divide both sides by 4 pi, if you divide this both sides by 4 pi, the mu naught over 4 pi is just equal to 10 raised to 7. Okay, and so with another units, so they are the same. You can use any or a number extracting this 4 pi times 10 raised to 7, but the big exact is use 4 pi. Okay, then therefore, again, if you divide this by 4 pi, then we have mu naught over 4 pi is 10 raised to negative 7 Tesla meter per amp. Okay, so therefore, again, if we remember the idea of remember, the electric constant is 1 over 4 pi permittivity. And if we okay, now 1 over 4 pi permittivity and 10 raised to 7, which is skinny. Okay, if you equate these two, substitute this value for the electric constant. No, sorry. The K is 1 over 4 pi permittivity. Okay? Then, the speed of light is exact, no? The square of the speed of light, C, is equal to 1 over the product of the permeability and permittivity. So if you substitute the permittivity value, which is, what is this? This is 8.854, the permittivity, 8.854 times 10 to the negative 12, and this one is 4 pi times 10 to the 7. If you simplify this, substitute everything, then you can use the speed of, you can calculate the speed of light, which is very close to 3 times 10 raised to 8 meters per second. So this is actually the exact relationship of the speed of light. So C square is equal to 1 over permittivity times the permeability. Okay, so here comes the problem. The problem says that we have the 6 microcoulomb, a point charge, is moving at a constant of 8, meaning the velocity is 8 times 10 raised to 6 meter per second. And according to the information, this is moving positive y direction relative to the reference frame. So there must be a reference frame at the instant when the point charge is at the origin. So the particle is at the origin of this reference frame. The question is, what is the magnetic field vector B? It produces at points, so different points, meaning the magnetic field is at point 0. Okay, and then we have x naught, then y is 0.5, and we have z 0.5 meters. So the question is, how much magnetic field? How much magnetic field B produced by the moving charge with this given information, position vector? Okay, so that's it, no? So we have this charge, and this is moving. If you consider this as x, y, and z, this charge moves upward towards positive y, and this is 8 times 10 raised to 10, and take note, Ch hat. So therefore, this is our V, velocity vector. Then the question here is, how much magnetic field produced at this coordinate 0, 0.5, and 5? So therefore, of course, meaning there's no y, there is no x. So this is x-axis. So this point is 0.5 here, upward, positive, because this is positive, and this is also positive for z. Z is towards you, so this is 0.5. So therefore, this is our point of interest. This is the point that we need to know how much is the magnetic field at that point. Okay, so remember, this is this area is lying on YZ plane because we have no x value here. So meaning it is a plane that generates from y-axis towards the z-axis. Okay, so that's why this is 0 for x, 0.5 for y, 0.5 for z. Okay, so of course you have to connect this from the source or from the origin towards that point, and this is our point of interest. So you need to find what is r, okay, vector. And remember, the requirement of calculating the magnetic field is we need the velocity and the position. So we have to, velocity is already identified, and we have to find this vector. So we need that area. That area generates, no? Remember, perpendicular to that will be what? Will be our magnetic field. Okay, so take note that the charge travels along y-axis, along y. Okay, so normal to this area is our magnetic field. So take note of the formula, mu naught over 4 pi. This is because this is vector, so therefore this must be a charge. Since positive na, then okay. Then take the cross product of the velocity, which is the velocity is 8 times 10 raised to 6 j hat. Then we need to know what is our r hat. So we have to find what is r hat, and we have this magnitude also. Okay. So first is our position vector is, of course, since we have already a yz coordinate. So since there's no x here, so our position is only 0.5 j hat plus 0.5 k hat. Then, of course, the magnitude is the square root of the squares of the components of y and k, 1z. Then, therefore, that's it. Then the answer is 0.707 as the r. So we have already r here. And we are still looking for what is r hat. So r hat is, remember the formula, vector, this one should be divided by r. And this one is 0.5 j hat, 0.5 k hat over 0.707. Then you have to simplify it, and the answer is this one. If you divide this one 0.5 by 0.07, 0.707, the answer is 0.0, and then you can double check this, 0.707, and also this one is 0.707. So this is now our unit vector, and we need to substitute it here. Okay, and that then we have r, put it here, and this velocity substitute it here, then simplify. Okay, that's it. This is our, the 10 raised to 7, negative 7 is our constant. You can ignore the unit to avoid complication. And the charge, according to the problem, is 6 micro. So therefore, this should be times 10 raised to negative 6 for the micro. Then this 8 times 10 raised to 6 j hat is our velocity. And we have to take cross product of that with what? With our unit vector. Then over r squared. That's it. So again, the strategy is you can move this constant away from this one, or take note that this is two terms, so you have to distribute. You have to first multiply this one, then we have that. But take note that if you multiply this, you are taking the cross product of j and j. So what is the cross product of j itself? It is 0, right? Cross product is 0. And this one is j cross I, cross k. It should be I. Okay? So therefore, you can have this result. This 0 is what? Because if you distribute this, if you take the cross product of this is j cross j, therefore it must be 0. Then the next term is 8 times 10 raised to 6. Okay? Then multiplied by this amount, this one. Then the j must be crossed with k. Take note that we give emphasis the vectors. No? These numbers are constant, so we can move it to the left, and we give emphasis to j cross k, because j cross k is what? It is I. So therefore, the answer is 6.79 times 10 to the 6 Tesla times I hat. So this is the answer to the problem. So the idea here is, in order to solve for problem, first is identify the velocity direction, and of course its value. So you have to find the velocity. Then after that, based on the condition of the problem, locate the position, the point of interest, where we want to know how much is the magnetic field. Okay. Then, of course, that's very important. Why? Because we need to find the unit vector and also its vector and its magnitude. So that's why this is now the process. After that, then we just simplify it from the formula. Substitute, of course, be careful of the cross product. Then these are the solutions of the problem. Now, sometimes you are given the angle. So if the given is angle and the question is what is the magnitude, then just take the magnitude of that. So we need only the angle, but most of the time you will be working with this vector. Now, if you're asked to find what is the magnitude, then take the absolute. The magnitude of this is, of course, this one, 6.79 times 10 to the 7, because the magnitude is the square root of the square since we have only one component, the square root of the square of this is just that value. If you have j here, then the square root of the square of x component is plus square of y component, and also with k component, then take square root, and that's the magnitude. Okay, so this is the answer. Solutions to the problem number 1. Problem number 2. In a Bohr model of hydrogen atom, the electron moves in a circular orbit. So the electron, of course, is circulating around the protons. Now, this problem says that the radius of circulation is 5.3 times 10 to the 11 meters, with a velocity of 2.2 times 10 to the 6. This is given to the problem, meter per second. If you were viewing the atom in such a way that the electron orbits is in the plane of the paper, so let us say the circulation is within the plane in front of you in the paper, with an electron moving clockwise, so it's a clockwise direction, you are asked to find the magnitude and direction of the electric and magnetic fields. So the two questions are coming from what is the magnitude of electric field and magnetic field that the electrons produce at the location of the nucleus. How will you answer this one? Okay, so of course, let us figure out the situation. So we have this electron, of course, negative value, negative charge. Then it is circulating, so this is moving in the clockwise direction with the radius given 5.3, and take note, electron has a charge of 1.602 times 10 raised to negative 19 coulombs, and the velocity of this motion in circular motion is constant velocity of 2.2 times 10 raised to 6. Then this is now the direction, because this problem says in a clockwise and they are on the plane of the paper, so it is circulating. And this point here is the actually location of the nucleus of the hydrogen atom. Then electron is orbiting around the nucleus. Okay, then therefore the electric field, there must be an electric field at the nucleus. Why? Because this is charge. Because negative, it is towards. So this is the question. How much is that magnitude? Then, aside from that, you are also asked how much is the magnetic field. Remember, magnetic field is curling. It is curling around the direction of the magnetic field. So if you can use your right hand rule, okay. So the right hand rule says that the magnetic field is towards the plane. So you can stretch your thumb, place it in the direction of your velocity, then curl your thumb. Then, of course, this is now towards the plane. That's why X. And this is the magnetic velocity. This is the magnetic field, while the electric field is towards the charge. So how much B and how much E? Okay, so let's start with electric field. The formula says 1/4 pi permittivity. So substitute the values. Since we have this constant, then you can replace the 1/4 pi permittivity. And the charge is negative, then since magnetic, you can take the absolute value of that, so 1.602 times 10. This is the charge of the electron divided by the position vector, or the distance, or the one, r, and this is squared. Then simplify, and the answer is 5.13 times 10 raised to 11 Newton per coulomb. This is the answer to the magnitude of the electric field. Then the direction is towards the electrons, so upward direction. Now, for the magnetic field, of course, we use the recent formula introduced in our lecture. So we have magnetic field mu0/4 pi, charge, absolute value because magnitude. Then, what are the necessary? This is 10 raised to -7. This is the electron charge, and we have the velocity given, and we take the sign of that. Okay, remember this sign, this P is the angle between what? In our discussion, this is coming from the velocity towards R. So what is the relationship? The velocity, remember, is what? Towards the right. then our R is directly below. So the angle is 90. So therefore, this P is 90. And R is given. Velocity is also given. So therefore, we can substitute the values here. Take note, 90 degrees. 1.6 for the charge, negative 0.2 times 10 to the 19 for the charge of the electron. So of course, take the absolute value, so in disregard. 2.2 times 10 raised to 6 is the velocity. You can ignore the unit because they are already consistent. And divide by R. R is also given in the problem. Then take square of that because this is according to the formula. Then simplify, and the answer is 12.55 Tesla. So these are the two answers, the electric field and the magnetic field. Okay, then this is towards the plane. So why? Because we use the right hand rule. And the problem also says find the magnitude. So meaning this is optional, the direction, because we are only concerned with the magnitude of that electric field. Okay, so these are the problems. So this is ignore this deadline. We are already on 2024. So solve this and submit this next meeting. We have this one. Then this is also included in the problem. Okay, so that's all for today. So thank you for listening.